All right, we're going to take a look at how to do a modified speed of sound activity at home. Normally we would do something like this in the classroom. We'd be using tuning forks and we'd use big pipes and tubes, and well, it'd kind of be a big thing. And actually it'd be really annoying because there'd be like 30 tuning forks all being used in the classroom at the same time, and it starts to drive me crazy after about 2 minutes. But here we can do it at home just with some simple tools. As I've got listed there, you're going to need to get a glass of water. Oh, that went right on my iPad. It's okay, glass doesn't conduct electricity. So a glass of water, a drinking straw. I'm using one that goes in, it's a kind of a big straw that goes in one of those drink bottle things. And it's just going to go in the glass of water like you're going to drink it, except you're going to blow air across it. And if you've ever done that at with a to-go drink at a fast food restaurant or something like that, you can blow across and make a whistle. That's what we're going to do. So we're going to use that and a ruler, preferably one with centimeters on it so that we can use convert to meters. And then you're going to need a frequency recorder, something that can measure the frequency. And this is where some of you might not be able to do this at home. Unfortunately, if we're using tuning forks, they have the frequency written right on there. But what we want to do, actually, hold on, let me get a napkin here. I'm going to clean the water off of my iPad screen here real quick. There we go. What we want to be able to do is use the equation V equals lambda times F. And in the lab setting, what we would do is we would measure just record what the frequency is as printed on the tuning fork. We would then figure out the wavelength using the straw and the ruler and everything. And then we would just multiply the two together. But now what we got to do is we have to actually measure this using the phone, which I do have. Sorry, phone is not spelled with an F. Measure this using the phone app, and I have a whole little video on that. If you don't like mine, there's probably dozens of others. And then we're going to use the ruler to kind of measure the wavelength. And then we can multiply them together to get an approximate velocity of sound. Now, velocity of sound in air, we've already talked about this. It's should be roughly 340 meters per second. We're going to be able to get to within about 5%, less than 10% off from that, using pretty rudimentary tools and using a property that you've probably played with before when you've got a drinking straw and a cup. You make a whistle, it's called resonance. Let's see if I can do it real quick. Yeah, that worked pretty good. So we're going to try to record that frequency, do a couple measurements, and then we can get what the speed of sound is. Now, why this works. Essentially, inside the straw, inside this drinking straw, when you get it to whistle or make a tone that at least sounds kind of like a tone, it's still going to be very airy. Essentially, you got a whole bunch of sound waves being created, but they're all very quiet. As you blow air across the drinking straw, those little air whoop-de-doos there, as you blow air across it, the air vibrates, and as the waves, the air compression waves move down the straw, they're going to hit the level of the water there and bounce back. They're going to essentially echo off of the water, but we're talking really, really low volume waves. They're very quiet. So the only way it's going to be loud and sound like it does when you blow across a straw is if the wave that's coming in is lining up with the wave that's reflecting, and we start getting constructive interference. You get that crest with another crest. High pressure area line up with another high pressure area, and if it does that at the right frequency, you get constant amplification of the sound, which is why if you change the length of the straw, you end up getting different tones. Gets higher pitch as it gets shorter because the waves that fit in that space are a higher frequency. They're going high pressure, low pressure at a greater rate per second, so you get higher frequencies with a shorter straw. The waves that fit inside of a longer straw happen to be bigger waves with lower frequencies, so they sound lower pitch. So there's really a lot of waves going on. I'm not doing anything different with my mouth. It's just when I make the tube a different length, I get a different wave fitting. So essentially, inside this space from the top of the straw down to the level of the water, we're getting what you could call kind of a partial wavelength. If we think that where I'm blowing across the top, that's where there's a lot of variation in the air molecules, you get something like a crest. And inside the tube, I essentially get a quarter of a wavelength. Remember that one wavelength has to include the crest and the trough, and then get back to where it started. So if I have a crest and then I just stop at the trough, that's a quarter of a wave. I still have a second quarter, a third quarter, and a fourth quarter to go. So inside that tube, I'm just fitting in the first quarter of a wave. It bounces off of the water, and then once it bounces off of the water, it comes back and it meets up with the next wave coming in, and it amplifies. Now, we want to, basically exploit that. So the next part is we're going to go through and take a look at actually doing this. Okay, we need to make a couple recordings. We need to measure the length of the tube right here. That's going to be capital L. Sorry, that's a crappy looking curly brace. Let's do this. Swoop, swoop. From the top of the water up to the top of our straw. That's going to be capital L. That's the length of what we're going to call a resonance chamber. So I just randomly filled up my glass of water. If you put the straw at the bottom, that's the easiest way to make sure you don't move it up and down. But if the straw is on the bottom and you blow across it and you're not getting a good sound like that, you can add some water or take some water out. But I'm going to measure how tall that straw is just literally by taking a ruler that's got centimeters on it and holding it at water level and measuring up to the top. Now mine is reading 15.5 centimeters. So I'm going to record that as L on my paper. Capital L is equal to 15.5 centimeters. Now you can do this in inches and with fraction, is it 7/5/16 or whatever the inches thing is. But this is convenient so that we can convert it into meters. And with meters, and I got my handy dandy TI replicator here, all we got to do is divide by 100 because there's 100 centimeters in every meter. So that's 0.155 meters. So I've got the length of my tube. Now, in order to figure out what the wavelength is, I need to take this number and I need to multiply it by 4. Because again, we're only fitting a portion of a wave in there because we want it to reflect back as the next portion's coming in. And so that's why we have to have only a quarter of a wavelength in there. Now, there's actually a slightly more detailed calculation to get this right. It actually does matter how wide the tube is here, but again, we're doing a quick version of this. We don't want to get too technical. So this is going to be within the 5 to 10% range of accurate. So if I blow across this, the frequency that you hear corresponds to a wave with the length the wavelength of 4 times this length L. So let's go ahead and calculate what that wavelength is. Got it on my screen here, multiply that by 4, and I get 0.62. So that means in this length of straw this big, I've got a quarter wave, so a full wave is 4 times that, 0.62 meters. That's it's just over half a meter, 62 centimeters long. It's not huge, but that's the size of one wave of that sound. Now we come to the tricky part. I've got to try to measure the frequency using that journal app. So I've got it on my screen here. I've got the frequency sensor going. I'm going to go ahead and try my best to blow across this, get some sound, and record it for you. And this is high-tech stuff here. Oh, that was a pretty good recording. Now, unfortunately, I screwed up at the end. You might be able to see it on the screen there. There's kind of a nice flat tabletop, and then when I dropped the straw, it spiked up really high. So I'm going to figure out what that frequency is. And according to my thing here, it says it's 501. So I've got a frequency of 501. Now, to me, that seems kind of low. I think I did this before, and it wasn't quite that low. But let's go ahead and calculate and see how close we are to the acceptable range of speed of sound is 330 to 340, like if we wanted to, actually measure things on across great distances. So let's go ahead and take that 0.62, and I'm going to, don't want the second feature. I guess I got to do it now. 0.62 times 501, and I get 310. Well, that's not too bad. 310 is a little low. It could be that maybe my measurement of frequency was off a little bit, but it's not bad. Okay, I'm off by about 30 out of 3, it's about 10% off. Let's go and try it again, see if I can get a better measurement. Sometimes, depending upon which, kind of like at what angle you've got the frequency sensor at, you might get different things. So here we go, making a fool of myself again. Well, that sounds bad. Try that second one there. So I'm going to measure that sound, and I'm getting, well, now it's saying 520. So obviously there's a little bit of variability, maybe how fast I'm blowing the air out of my mouth. So instead of 501, now I'm getting, or 520 hertz. So high-tech equipment from Google. So if we recalculate using that, let's see what our spread is. So 0.62 for the wavelength times 520 for the frequency, and I'm getting 522. So I'm off by 18 out of 310. So we're much better range there. So I'm getting a wave speed that's someplace between what I have before, like 310 or 322 meters per second. That's pretty darn close. I mean, to be able to measure the speed of sound just using a straw and an app on your phone, that's pretty cool. Something that can travel 3.5 football fields in a second, and you can measure just using some everyday stuff that you got laying around the house. So give that a shot. Totally just like kind of a cool activity to try out. See if you can get good results, if you can get way better results, if you're really close to 340. Like if we were in the classroom in the lab, people are like dead on 340, 342. I mean, it's like really good. So at home, give it a shot, see what you get. Nothing can go wrong, right? And you can drink the water when you're done. Don't waste it.